Okay, we are in Google Colab, that is an online platform for Python. It's really like Jupyter Notebook. I will leave a link in the description to download this code. So I won't go into every detail of the code, but I will just point out the most important parts. Let's have a look at the index. In the first step, we are going to import the relevant libraries. In the second step, we are going to create the data, the inputs data for our Black Scholes model. In the third step, we are going to compute the option prices given the Black Scholes model. In the fourth step, we are going to preprocess the data. So at that point, we will be ready for the fifth steps, in which we are going to perform a very easy linear regression on the input data. In the sixth step, we are going to perform the real deep neural network training on the option prices, and we will analyze and test the results in the last step, in which we will leave some space for further considerations. Okay, let's import the libraries. It's nothing difficult, but please do note that we will be working mainly with pandas, with NumPy, and with TensorFlow. Here we create the data that will be used as inputs for our Black Scholes model and for our deep neural network. We are going to create 10,000 observations. Here we define the extreme of the range in which the stock price will be defined. So the stock price will be comprised between 1 and 1,000. There is a little variation of this for the strike price, because the strike price will be defined as a percentage of the stock price. So here you can see its multiplying factor. The strike price will be comprised between 80% and 120% of the stock price. The time to maturity will be comprised between 0.1 and 10 years. The risk-free rate between 1% and 10%. The standard deviation between 1% and 30%. We are now generating the input data using a random uniform distribution in NumPy. As you can see, for the strike price, we multiply this random uniform distribution of k time the stock price. And we go on for the other variables. And here you can see the result. Here with the .describe command, we are getting some descriptive statistics of our data, like the count. We have 10,000 observations as expected, like their mean, like their standard deviation, and so on. At this point of the video, we are ready to create the call option prices using the Black Scholes formula. And in fact, this part of the code is exactly the Black Scholes formula written in Python code. If we run it, we will obtain another column, the column C, that is exactly the call option prices. Now we can also inspect the data using this command here, the SNS pair plot command. It takes a while. Okay, so this command plots all the features against all the other features. So in this case, we have C, the price of the call options, that is plotted against C itself, S0, K, the time T, R, and the standard deviation. It's a kind of first check, because you can already see here some of the relationship going on between the option price and the other features. Now we are going to preprocess the data. The first thing we have to do is to split our dataset into a train dataset and a test dataset. So here we are defining our train dataset as 80% of the initial dataset. Then the test dataset is defined simply by dropping from the initial dataset the train dataset that has been previously obtained. Here we are separating our features from our labels. We are going to do that both for the train and the test dataset. So first we do a copy of the two datasets, and then we use the method pop to extract the column C, the column of the call option price, and we store it into the train and the test labels dataset. We run it. Okay. Okay, now we are going to normalize our data, also known as standardization of data. So first we create our layer. I called it normalizer. So from preprocessing, we use the normalization layer, and then we adapt it to a NumPy array of the train features. This is done to adapt, so to fit the normalizer layer to our data. In the end, we can check the result of the normalizer simply by applying it to our train features. And in fact, if we describe it, we can see that our feature now have a mean that is very close to 0 and a standard deviation that is almost exactly 1. So our normalization procedure worked.